Yo, this is the LC101 DeCal. I'm Richard, one of the TAs. We'll be doing min stack. Alright, so our job in this question is we're gonna design a stack. And the only way that it's different from just a normal stack is that we want the additional functionality of being able to retrieve the minimum element of the stack in constant time. So we have push, pop, and pull. They call it top. And then in addition to that, we have this get min function. Okay, so we're not going to be able just to implement like a stack and that's it. We need some way to keep track of the minimum element in the stack at all times. And preferably, we want to do that in like constant time. Obviously, you could just call min on a list and that'll get the minimum, but that takes linear time. That's like too slow. We want to be faster than that. So we have a doc test here. And why don't we just go through like this example? So imagine that our stack is here. I'm going to go from like left to right. So the bottom is on the left. And then, no, get out the way. The bottom is on the left. And then to the right, we add elements onto the stack. So initially, you can see in this example, the first element we pop is -2. And let's say after we push -2 onto the stack, like what is the minimum of the stack at this point in time? Well, it's just -2 because there's only one element in the stack. That's the minimum. Okay, and then after that, let's say we push 0. And at this point, like what do we want to do? Well, we've added another element onto the stack. So we need to like consider whether that changes the minimum or not. So in this case, 0, it's not less than the current minimum, so the current minimum just stays the same, and it's -2. Alright, and then next we push -3. So like -3, we push that onto the stack, and now we want to consider whether the minimum has changed. So again, how can we like tell whether the minimum has changed? Well, the minimum up to this element is just going to be like the minimum of the past elements and this current element that we've pushed, because the minimum of all the elements to the left and the minimum of all the elements to the left and the current element is going to be the minimum of all the elements. So instead of like, you can kind of see that we don't have to go through all the past elements. All we just have to do is look at the minimum of the last element and then compare that to the current element that we just pushed. And in this case, it's -3. Now, let's say like we pop off -3 from the stack. So if we delete -3, the minimum element is no longer going to be -3 because it's not there anymore. And it's going to be, the only elements that we have left are -2 and 0. So how do we know what the minimum element is of -2 and 0? Well, we already like recorded that earlier. We've noted that it was -2 at this point. So you can kind of see that the minimum element for each like element in this, for each like size of the stack will just be the minimum element of everything, including it and to the left. So as long as we just like maintain all these numbers as we like include elements, as we push elements, as long as we maintain the minimum element of that like of the stack at that point in time, we will know what the minimum element is for each, like no matter what the size of the stack is. So we don't have to ever look through the rest of the list, or not the list, the stack, to find the minimum element. We could just keep track of it as we go along. And as you can see, if we want to pop -3 off the stack, all we need to do is just pop the corresponding minimum at that point with it and just delete it. And we'll see that the minimum now is -2. We've like reverted back. So what this suggests is that in addition to keeping a stack of the current like elements that we have, we just need to keep a like corresponding stack that's like symmetrical to it, except it will maintain the corresponding minimum at that point in time. So let's just implement that. So again, with the example, if we push -3, we just update saying like after we push this -3, -3 is the minimum of everything to the left, including this and to the left. Okay, so let's implement this. So we're gonna have one stack that actually has the values, and then we'll have one stack that has the corresponding minimum at that point in the stack. So we'll just initialize self.vals to empty stack, and then we can initialize self.mins to a corresponding empty stack. Now, when we push, we want to push x onto the stack. So we'll push x onto self.vals, and then also we want to we want to update our current minimum. So after we push x, the minimum is either going to stay the same or it's going to be x. So what it will be is either x or the previous minimum, in which if it's the case that x is not smaller than all the other elements to the left. Okay, now this is an issue because we have a -1 here, and initially the list is empty, so we'll get an index error. So initially we can think of the initial minimum as like infinity, and then this is kind of like our buffer just to compare when we have no elements. X is going to be the minimum. Okay, now when we pop, we'll just pop from I guess they don't want you to return it, so we can just pop it. So we'll just pop from vals, and then also we'll just pop from mins. Okay, now when we get the top value, that's just the same as you normally do with a stack. Return the top value. I don't think we have to deal with the case where there's no elements. Yeah, it's fine. All right, and then to get the minimum, well, we're basically keeping the minimum as we go along. So when a stack has since we're keeping track of it as we go along, all we have to do is just return the current minimum, which will be the most recently added minimum. So we can just return self.mins and then return the top of that stack. And I think that's it. Nope. Oh no, just comment that out. Okay, yeah, that's all.